This conference will now be recorded.
And then we are seeing their single component system phase diagram. This is the vapor pressure line for ethane, and this is the vapor pressure line for heptane. And in these two, we may see the different percentage of these two components. Okay, so we may have 10% of C2 and the remaining can be C7, and we will have a phase envelope which will just give us the two-phase region. Two-phase region means that I will have gas and liquid in the system. If the reservoir pressure and temperature, if this is my reservoir, if the reservoir pressure and temperature falling into this region, then I will have liquid system. If it is falling into this region, then I will have a vapor reservoir, and these will maintain the miscibility. But if I'm falling into the phase behavior, phase envelope region, then I would not maintain 100% miscibility. So that's why if I would like to have 100% sure, if I would like to have miscibility for this system, I should be avoiding to stay inside the phase envelope in terms of pressure and temperature in the reservoir. So I need to increase the temperature, or I need to increase the pressure of the reservoir to be away from this zone to maintain miscibility. And when we are coming to multi-component system, and the story is very similar to two-component system. And we know what multi-component system, we examine it in our profession by considering 5 different reservoir types: dry, wet gas, retrograde gas, volatile oil, and black oil. And so we need to be away from the phase envelope region for these multi-component systems as well. So what we said, we have here pressure and temperature change. But with the change in the pressure and temperature, I can maintain miscibility in the system. So here is another example showing us how we can maintain miscibility. And here I have an initial oil composition given as 40 mole percent butane and 60 mole percent decane, and I am putting this composition on a ternary diagram. So this is my two-component system, and this is my initial oil, and I would like to recover this oil by injecting carbon dioxide to this reservoir. So my question is, can I maintain the miscibility? So if I will increase the reservoir pressure to 1900 psi, this is my phase behavior, which is given with the ternary diagram for three-component system. What I'm doing, I'm just plotting a line between injection fluid and the initial oil, and I'm seeing if this line is passing through a two-phase envelope. And I'm not seeing any two-phase envelope in this phase diagram. That's why this is 100% miscible, and that's why I'm getting a really high recovery. And if I would like to lower the pressure in this experiment to 1700 psi, so I'm seeing a kind of a two-phase envelope formation here. Okay, so if I will plot a line between carbon dioxide and initial oil composition, this line is passing through the two-phase region, which means that this is not 100% miscible, but it is multi-contact miscible. Why? Because my initial oil and the carbon dioxide is just falling into the opposite side of this limiting tie line. So I would like to lower the pressure more to see if I can still maintain more miscibility, multi-contact miscibility. And what I'm seeing here, 1500 psi, I'm seeing that the phase envelope is just getting bigger. So this is my two-phase region. And once I am just plotting a line between injection fluid and initial oil, it is passing through the two-phase envelope, so I cannot maintain miscibility. So which means that this is a miscible process, this is immiscible process, but this is multi-contact miscible process. So if I can maintain first contact miscible, I'm getting the highest oil recovery. So why I'm preferring miscibility? Because I'm getting higher oil recovery. That's why I prefer miscible flooding over first contact miscible flooding over multi-contact miscible and immiscible processes. And this is just showing how phases are changing and how miscibility is changing with the change in pressure. And if people play with the temperature, again, the phase will change and miscibility will change. Apart from pressure and temperature, what else can change the phase? Composition can change the phase. So here we are seeing 3 examples. And this example, the first example is miscible flooding. The second example explains this is immiscible flooding. These 2 are miscible flooding examples. Let's see through this example. Let's say our reservoir is 2000 psi, 150 Fahrenheit. For that condition, this is representing my oil, which is in liquid phase, and I would like to recover this oil by injecting methane. And I learned in the previous slide that if I will maintain miscibility, then I will recover more oil for sure. So what I'm doing, I'm just checking their phases at atmospheric condition. Both methane is in gas phase and oil is in liquid phase. And I'm bringing them to the reservoir temperature and pressure, 2000 psi, 100 Fahrenheit. And methane is still in gas phase and oil is in liquid phase. And once I am mixing these 2 components at the same pressure and temperature, I'm seeing that they are not miscible. And the mixture is giving me 2 phases, gas and liquid, and multi-component system. And the oil, I have several components, plus I have methane in this mixture. Now, I would like to check if I will inject, instead of methane, propane, if something would change. This is at atmospheric condition. Oil is in liquid phase, propane is in liquid phase. Then I'm bringing this to the reservoir pressure and temperature. And what I'm seeing, propane is becoming liquid. It was gas, atmospheric condition. At reservoir, it is in liquid phase. Once I'm mixing these 2, what I'm seeing, the mixture has just 1 phase, which is liquid only. And this is first contact miscible process. And let's check the miscibility of propane and methane right now. Propane and methane are in gas phase at atmospheric condition. And what I'm doing, I'm just bringing them to reservoir temperature and pressure. And I'm seeing methane is still in gas phase, but propane has changed its phase from gas to liquid. If I will just blend them in a container at this pressure and temperature, then my mixture is 100% miscible, and the mixture is in gas phase, even though propane is in liquid phase. So I would use a trick here. Okay, so let's try to understand the reservoir case one by one. So this is my reservoir case, this is my injection well, and this is my production well. Let's say 2 vertical wells, a simple representation. And if I will inject methane to this oil reservoir, I will have immiscible flooding, which is known as secondary recovery process. If I will inject propane to this reservoir, then I will have a miscible flooding, which is an enhanced oil recovery, tertiary recovery process. However, propane is really expensive when compared to methane. Methane is abundant. We are producing natural gas. So I'm insisting on injection methane. Can I still maintain the miscibility? Yes, I will use a little bit trick. And what I would do, I would just inject a little bit like propane layer and then methane. Propane and oil are miscible, as we discuss here. And I know that methane and propane, this interface is miscible. So this is also first contact miscible process, but I use a trick, engineering trick, to minimize the cost of the process. Okay. So now we have seen some methane, propane, those kind of things, but how we will really select the right solvent for our process. Now we will go in a little bit deep into this. So we know that right now it's giving us a lot of headaches, that the carbon footprints of the petroleum consumption is giving us a headache. So can we just get rid of this headache by just making carbon dioxide a solvent? And what we are seeing, carbon dioxide is a greenhouse gas, and everybody is talking about that. It's a kind of a bad guy, so we need to get rid of carbon dioxide. Can we inject carbon dioxide under the ground as solvent? Yes, actually we can inject. Apart from carbon dioxide, what we can inject? What about natural gas? And in natural gas, we are producing mainly methane. What about methane? Is it also a greenhouse gas? And when I'm looking into global warming potential of these two gases, actually carbon dioxide is really innocent when compared to methane. The carbon dioxide, if we are producing carbon dioxide 400 ppm, if we are exhausting 400 ppm carbon dioxide to the atmosphere, its global warming potential is known as unity. And what about methane? If I will release 1.74 ppm methane to the atmosphere, it has a global warming potential 84 times more than carbon dioxide. So methane is also a really good candidate for injection, so we can just minimize the environmental impact of carbon dioxide and methane and the global warming impact also, these two gases. Let's see if they are miscible with the oil or not. So again, we need to look into the phase diagram. So this is a ternary diagram, as we discussed before, and this is plotted at constant pressure and temperature. And I have the injection fluid here, which is methane or carbon dioxide. C1 is methane or carbon dioxide. And I have here the components of the oil. And heptane plus components are here, heavy components are on this end, and the intermediate components are on this end. So my oil composition will fall somewhere here, okay, on this line. And then I'm planning to inject either carbon dioxide or methane to this reservoir at this pressure and temperature. And I would like to see if I can get a kind of a easy miscibility with the injection of either carbon dioxide or methane. So what we were doing, we were just plotting a line between the injection fluid and the oil composition. If my oil composition is somewhere here, closer to the intermediate, if I have more intermediates inside the crude oil, then these will maintain a better miscibility. But if I am on this end, if I have more and more heavy components, then it is almost impossible to get miscibility with both that I'm injecting. But if I'm in between these two, which one is having more advantage? As you can see, the two-phase envelope of carbon dioxide is given with green, and the two-phase envelope for methane is given with red phase envelope. Methane phase envelope is greater than the carbon dioxide phase envelope at constant pressure and temperature, which means that with the methane, it is less likely to get miscibility, but with carbon dioxide, I have more hope. So this is at constant pressure and temperature. Let's check with the varying pressure and temperature for different hydrocarbons. So each concrete and black lines are representing the vapor pressure line of each single component. So this is for methane, this is for ethane, propane, normal butane, normal pentane, and it continues like that. If I am planning to blend methane with decane, then my phase envelope is really big. But if the differences in the carbon number is getting smaller and smaller, the phase envelope is getting smaller and smaller. So which means that, let's say I have a decane reservoir and I would like to just recover this reservoir by injecting methane. And this is my phase envelope. But we don't have a decane reservoir. We have some oils heavier than that, and it's somewhere here, which means that with methane, I will have a worse phase envelope for the real oils. So in order to maintain miscibility, I need to be away from this phase envelope, and it's somewhere here. I need to increase the pressure of the reservoir really high if I will insist to maintain miscibility by injecting methane, or I can increase the temperature really high in the reservoir so I can still maintain the miscibility in the reservoir. Instead, what I'm seeing, carbon dioxide has a reasonable phase envelope with the higher molecular weight hydrocarbons. So I have better chance with carbon dioxide rather than methane. Sorry. Okay. So we started to talk about oil, real oils, and these are not real oils, just giving us an idea how miscibility is really difficult with these two greenhouse gases. So if I would like to just go into the real oil, carbon dioxide seems like better than methane, but can I still maintain miscibility with carbon dioxide? Actually, not in every oil. Especially in heavy fractions of oil, carbon dioxide is immiscible, and it is creating another phase under the ground. So we were till here, we were considering two phases, liquid and gas. However, with the presence of heavy fractions and its interaction with carbon dioxide, I may create the third phase, which is the solid phase of hydrocarbon, and it is known as asphaltenes. So asphaltenes are really a common problem in oil industry, and we are not only seeing in heavy oils this problem, actually we are seeing more this problem in lighter oils. Okay, and here I have the reservoir condition, reservoir pressure and temperature, while I am producing oil from a light oil reservoir, from a conventional oil reservoir. The pressure and temperature follows this line in the pressure and temperature. And what's happening, it is going into phase change, even though you are not adding any component, and because of the change in the pressure and temperature, you are creating liquid, vapor, and the solid phase in the reservoir, which is known as asphaltenes. And this will be enhanced if you are injecting something which is insoluble in asphaltenes, such as carbon dioxide. So what I said, asphaltenes are really huge problem in the oil industry because they are plugging the pores and causing formation damage, and they are causing wettability alterations by changing the wetness of the surface, rock surface, to oil wet, and causing some flow assurance problems by blocking the pipelines. And what is asphaltenes really? By definition, asphaltenes are insoluble in normal alkanes, but soluble in aromatic solvents. So you are seeing here 3 oil samples and their solubility and different normal alkanes. What I said, it is insoluble in normal alkane, and I'm treating these 3 samples with normal pentane and normal heptane, normal alkanes. And what I'm getting different amount of asphaltenes in different oils. And once I'm changing the N-alkane type, and again, the asphaltene type is changing, amount of the asphaltene is changing as well. So what I said, it is insoluble in alkanes, and these N-alkanes are giving different amount of asphaltenes with different polarities. So here we have C1 to C7, how the asphaltene precipitation is changing. Asphaltene precipitation is decreasing with the increase in carbon number in N-alkane. So this is the first portion of the asphaltene definition, and the second portion is giving me some hope about miscibility. So the second portion is saying that asphaltenes are problematic, but they are soluble in aromatic solvents. So what is aromatic solvent? This is an aromatic ring, and this chemical is known as toluene, and you may find this chemical in some stores. You can buy it easily. And let's see the toluene, if toluene miscibility is promising or not. So this is my oil and sand mixture. It looks like consolidated before I inject toluene to this core. And after I inject toluene, what's happening? I'm sweeping most of the oil and I'm making it unconsolidated as well, because the consolidation is maintained by the solid phase, which is known as asphaltene. And because asphaltenes are soluble in aromatic solvents, then I'm just sweeping away the asphaltenes as well and making my reservoir rock extremely unconsolidated. So this seems like really promising, but I have problem. And the problem is, first of all, aromatic solvents are extremely expensive. And apart from their cost, they are flammable and they are hazardous and harmful. So it is a good option to recover more oil, but because of this reason, we need to find another way to deal with the solid phase of the crude oils. So what we said, first contact miscible processes are the best miscible processes to get the maximum oil production. And what we have seen that aromatic solvents are giving the highest oil recovery because of their high solvent power. And they are reducing the viscosity of the oil and reducing the residual oil saturation significantly. But our problem is these are expensive chemicals and they are toxic chemicals. So what we said, okay, we would like to have more challenge and we would like to recover the dirtiest oil by using some environmentally friendly solvents. So what is the dirtiest oil? And so this is the oil resources that we have. This is the conventional oil resources, and the remaining oil that are trapped in a conventional rock are oil sand, extra heavy, and heavy oil. So here you are seeing those pictures. They are nasty oils, okay? And how we are categorizing these oils by looking into API gravity measured at standard condition and the viscosity measured at reservoir temperature. So this portion of the graph represents the light oil, conventional oil. And if my oil has an oil viscosity at reservoir condition 10,000 centipoise, over 10,000 centipoise, I'm not looking into API gravity, but I'm calling it bitumen, okay? Because this is my oil flowing limit in the reservoir. And below oil flowing limit, I'm making my categorization based on the API gravity. Here, 10 API gravity is critical because 10 is the density of water. If my oil is denser than water, then I'm calling it extra heavy oil. And if it is lighter than oil, then I'm calling it heavy oil. So in this presentation, I will show you the results that we obtained from two different oil samples. And you are seeing here the first crude oil sample. It is extremely nasty. It has at around room temperature 40,000 centipoise viscosity. And the second oil significantly lighter than, but still because of the viscosity is 400 centipoise, it is a heavy oil. And once we are checking these asphaltenes, this has really high asphaltenes, and pentane insoluble asphaltenes. This has significantly low asphaltenes. So we try to recover this two oil by using a miscible flooding process, and our target was to create first contact miscible. We were not trying to recover these oils by using multi-contact miscible processes. So we tested three solvents. So we tested lemonane and pinene, and also we tested carbon dioxide. So these are all environmentally friendly solvents. We are trying to get rid of carbon dioxide from the atmosphere. And these two are edible solvents, which means they are citrus-based, so you can drink it, you can eat it, and their chemical formulas are, close formulas are the same, but the molecular structures are different. And you will see that they will create different results. So what we did first, we just blend these new chemicals, and till coming here, we tested a lot of environmentally friendly solvents, so-called, that they didn't give any recovery. So I'm just giving here the best results that we obtained till now. And what we did, because these were new chemicals for us and mostly for the oil industry, first we just blend this and measure their viscosity by using a rheometer. So this is a rheometer, which is measuring the dynamic viscosity. It is not measuring the kinematic viscosity, but we can just convert dynamic viscosity to kinematic viscosity easily. And you will see here the viscosity comparison once we are just blending crude oil and solvent to 1:1000 ratio, which means that if I'm adding 1 barrel of solvent to 1000 barrel of oil, and these are the viscosity reductions for the oil 1 and oil 2. And the black curves are representing the initial oil viscosity. Red curves are representing when we are blending initial oil with toluene and at this ratio. Green curves are representing when we are blending initial oil with this citrus-based chemical, lemonade. And when we are mixing initial oil with the pinene, another citrus-based chemical, we obtain this blue curve. As you can see, what we said initially, toluene is an extremely strong solvent. It has a high solvent power, but here, this is my initial oil viscosity, and with toluene addition, I'm decreasing the viscosity significantly. However, for this oil, I'm increasing the viscosity. So the mechanism of the toluene is really different from oil to oil. When I am checking for the lemonade and pinene, what I am seeing that even though for oil 1, toluene gives best viscosity reduction, also these two, the environmentally friendly ones, are increasing the viscosity of the oil 1. And for the oil 2, I'm seeing that the lemonade is really giving promising results and making this oil more movable. And again, lemonade and pinene are edible, so they are extremely environmentally friendly chemicals. So what we have done, we just did the miscible flooding test in our laboratory. So we have a core flood. It is just 1 feet long, and it's right here. And we injected this core, either a liquid solvent or a gas solvent or the combination of liquid and solvent. Which ones are liquid? Lemonade and pinene are liquid, which is gas solvent. Carbon dioxide is gas solvent. And how we prepare the samples by just blending oil and sand and water in this percentage in the pore space. And we maintain the back pressure as well with nitrogen injection. And then we collected the produced oil samples, and we just check the injection rate of the solvent. And this is incorrect. So, and the carbon dioxide injection rate by using a computer and the data logger. So in the first, we tried on the first oil 4 different core flooding shames, and this first one is the pinene injection. Then we injected lemonade. Then we injected carbon dioxide and lemonade together, and we injected carbon dioxide and pinene together. And you are seeing here the cumulative oil production for those cases for barrel per acre foot reservoir. And what we are seeing here, pinene and lemonade are really good. But if I am blending them with carbon dioxide, the mechanism is changing a lot, and it's not giving that high oil recovery. So if I would like to see it with the percentages, again, I'm seeing that the pinene is really giving higher results than lemonane, but lemonane is also good. As a petroleum engineer, I need to check also the economic side, and I'm seeing that the pinene is really expensive when compared to lemonane. So I'm saying for this reservoir, my recommendation will be injecting lemonane to recover this reservoir because it is cheap, it is environmentally friendly, and I'm using less lemonane to recover more oil. And once I'm checking the oil two, which has significantly lower viscosity when compared to oil one, here are the results. So this is the just carbon dioxide flooding. As you can see that sweep is almost nothing. And if we are injecting lemonane, if we are combining carbon dioxide and lemonane together, if we are first injecting carbon dioxide, then switching to lemonane, just pinene flooding and carbon dioxide and pinene flooding all together. So the pictures of the post-mortem after the experiments also showing how we are getting clean recovery of this oil after the injection of these new chemicals. And once I'm just checking the best case in terms of oil production, 76%. And the cost of the solvent, I can easily say carbon dioxide plus lemonane altogether for this oil reservoir will yield the best oil recovery. So throughout this presentation, I gave a lot of information and there are a lot of questions even in my mind. So I would like to just try to clarify some of them by using some enhanced oil recovery concepts. I know that many petroleum engineers are graduating without getting an enhanced oil recovery class, but it is very important to know some important numbers, and we will be reviewing those important numbers on these experimental results. So first we started testing these new chemicals by just doing viscosity measurements. And in the viscosity measurements, we have realized that lemonane and pinene viscosity, when I'm blending them at the surface with the oil, they increase the viscosity of the oil. This is my initial oil, and this two promising solvent is giving me higher viscosity. But while I'm conducting a flooding test, I get more oil recovery with this too. And the post-mortem pictures are also telling me the same thing, okay? So these two are extremely efficient recovery, and we tested also carbon dioxide with this oil. There is no hope. We tested carbon dioxide for a week. So these experiments are taking like 4 hours to complete. With the carbon dioxide, we did a test for 1 week, and we even didn't get a drop of oil recovery, but just carbon dioxide injection. So I'm seeing that pinene and lemonane in the core flood experiments are giving really promising results, but in the viscosity measurements, it's saying vice versa. So what's going on here? Really, I don't understand this. Here, the reservoir rock is also playing an important role in the mobility of the oil. So in any enhanced oil recovery processes, we need to evaluate two important numbers, capillary number and mobility ratio. And many petroleum engineers are graduating without knowing these two numbers, and they are learning these numbers while they are in the oil industry. These are very important numbers because they are showing the efficiency of the process itself. Capillary number, we are looking for high capillary numbers, and we are trying to make it like infinite if we can to increase the pore scale displacement efficiency. In the pore, to reduce the residual oil, we are trying to do that. And the mobility ratio is, we are looking for a mobility ratio less than 1 to enhance the volumetric scale sweep efficiency. So in 3D, I'm looking into this, and the macroscopic scale, and the minimal scale, I'm looking for the capillary number enhancement. So while I'm looking into these two numbers, I'm seeing here contact angle, I'm seeing here relative permeabilities. So these two are also related to the rock properties. Especially the contact angle is telling me more about the wettability, like relative permeabilities as well. So how wettability is changing is affecting my oil recovery. And the wettability concept is coming into place when I am including rock into my experiments. So here you are seeing some wettability examples, and just to refresh your knowledge, if we are having a contact angle closer to 0, then I am going towards the strongly water wet reservoir, and if I have a contact angle closer to 180, then it's representing more like strongly oil wet condition. So you are seeing here at the top silica surface, which means like, let's say sandstone reservoir, and this is my calcite surface, let's say a carbonate reservoir, calcium carbonate reservoir. I have here water droplets given with blue, and I have also here oil phase. Okay, these dash lines, these areas, dashed areas are representing my oil phase. And what is my oil phase here is isooctane. What is my oil phase here is given here. And then I have isoclane, which is an aromatic hydrocarbon with nitrogen attached to it. And you're seeing as an oil component naphthenic acid. So you may just not understand why I'm calling these oil components. These are all petroleum products. So they are processing in the refinery. After we just produce the petroleum, we can get these components. So these components inside the petroleum. And what we know as sandstone, we know that it is water wet. And for calcite, what we know, it's in general oil wet. But these examples are showing me that if my oil composition is changing, their wettability is changing as well. For example, if I have more aromatic structures, sandstone surface is becoming more oil wet. And if I have more straight chain hydrocarbons in my crude oil, then the calcite surface is showing strong water wet conditions as well. So what is happening here is not only related to the viscosity reduction of the oil, but also the interaction of the oil with the rock surface. And we are seeing that interaction with the core flood experiments better. So when we are coming to other minerals exist in the oil, let's say like clays. So clays are really not giving good results in general, and they are causing a lot of problems in the reservoir, and they are changing the miscibility as well while we are trying to conduct some miscible flooding experiments. So here I have another oil sample that I haven't shown you before, and this is we are injecting here toluene to recover the oil inside just sandstone, and inside sandstone plus clay 1, or inside sand plus clay 2. So clay 1 is kaolinite, clay 2 is kaolinite plus illite. As you can see from the post-mortem pictures, that the illite is really making the rock extremely cemented and blocking the pores and reducing the oil recovery significantly. And this is just one-dimensional laboratory case, and think about in the reservoir how it will end it. So while we are approaching to miscible processes, we will look into phase diagram, but at the same time we need to look into their interaction with the reservoir rock. So, and the trial errors should be done only in the laboratory, not in the field, because the consequence of these processes can be extremely catastrophic. So I will show you 3 case studies. The first one is representing water flooding, and here we are doing water flooding. We are conducting 3 water flooding tests on 3 different reservoir rock, and we are observing similar behavior on 3 reservoir rock. And first, we are just injecting 2 feet per day water to recover the oil, and we are just seeing 42% oil left behind. If we increase the water rate from 2 to 200, then the residual oil is just reducing significantly, 10% more oil we are producing. So because this is too much, we can just say that let's start with the 2 feet per day water injection. Once we reach the maximum oil production, then switch to 200 and increase more the oil recovery. So it might be the plan, but what's happening till reaching 2 feet per day, we are trapping the phases under the ground. And then once we are switching to 200 feet per day, after this injection, we could just recover 4% more than the initial case, okay? And the remaining 6% will remain under the ground, and it has been trapped, so you cannot recover it anymore. So this trapping is irreversible. But it is good to see this before applying in the field, because this 6% in the laboratory is maybe 6 milliliter oil, but in the reservoir it might be 6 million barrels of oil, 60 million barrels of oil. So it is good to do this kind of test in the laboratory before application. And the second is the polymer flooding case. Here you are seeing we are injecting water because water is cheap, and then we are the first one is water flooding. The second one is polymer flooding with this variation in the viscosity. So we just increase the viscosity of the water by adding polymer in it. And the residual oil, as you can see, that decreased a lot. We got more oil, 18% more oil than water flooding. So this is a good idea, but polymer is expensive. Let's start with water flooding, and then once you reach the maximum oil recovery, then switch to polymer flooding. What would happen? So you are just recovering 1% more than only water flooding. And what happened to the remaining oil? You trapped it, so you cannot recover it anymore. It is not easy to get from the ground. Another example is surfactant flooding. So this is just water flooding. If you will do surfactant flooding with a kind of a really low interfacial tension surfactant, then you're enhancing the oil recovery a lot. And again, surfactants are expensive. Let's start with the water flooding. Once you reach the maximum oil recovery, then switch to surfactant. And what's happening? You're just recovering again 1% more with this switch. So, which is not making that much sense. However, this kind of things may change, and you may enhance the oil recovery with this switch. Before you are doing this in the field, you need to do it in the lab to see which one is the best way to go for your oil reservoir. So let me just conclude my presentation with a couple of concluding remarks. So phase behavior is really very difficult to understand for complicated multi-component system like crude oils, and you are adding some solvents to recover that crude oil. And there are also the contribution of the reservoir rock to better understand the miscibility. If the miscibility will happen in your reservoir, so it is better to conduct miscible flooding, core flooding tests by considering the real reservoir oil, by putting in your as a sample in your core holder real reservoir oil, reservoir rock, and reservoir water as well. I didn't show the impact of water salinity in the reservoir, and it will have an impact as well. And you may understand the impact of the solvent, effectiveness of the solvent by doing some quick viscosity measurements. But again, once the reservoir rock is involved, you may get amazing and different results, because because of the transport in porous media phenomenon happening in the during any flooding process. So I would like to thank to my research team at Texas A&M, which is heavy oil shales, oil sands, and carbonate analysis and recovery methods research team. And I would like to thank you for your attention. And if you have any questions, I'm glad to answer them. Thanks a lot.
Thank you, Dr. Berna. This was really quite a information-packed session with a lot of different aspects covered. No, it was absolutely great for beginners, intermediate, and even experts. So at this point, if you have any question, you can either type your question in the chat box, or you can just come off mute and ask it to Dr. Berna directly. So we'll give the floor to the participants.
Dr. Berna, thank you so much for the excellent presentation. Very informative, like Audi said. So my question was kind of like when it came to mixing the solvent, the CO2 and limonene and other mixtures, was the CO2 supercritical, or was it like CO2 in the vapor phase?
It is in the vapor phase.
In the vapor phase, okay.
Yes.
I was wondering if you did that. I was actually thinking you would get to, there was going to be a sample of CO2 and methane mixture actually being used to float to see how it's, because I know in the other part of your presentation you stated how methane would require very high pressures or very high temperatures to attain or maintain miscibility, and I was just wondering if it was a mixture of methane and CO2, how that system would look like.
So this is kind of a part of a sponsor project. I didn't mention that. Once the sponsor came to us, they said, we cannot increase the reservoir pressure. We cannot play with the reservoir pressure. And we really have to have something environmentally friendly. We cannot have anything like toluene in the reservoir. And in the first place, what is in our mind is carbon dioxide, but we know that it is not miscible. But we are still wondering at reservoir pressure and temperature if immiscible flooding even will maintain some oil recovery. And what we have shown that no way it will not recover even a drop of oil with the carbon dioxide flooding. This is why we didn't use the supercritical carbon dioxide first, because of the sponsor need. And the second, because carbon dioxide didn't get anything, and they have some carbon dioxide available in their hand, they wanted to inject carbon dioxide, and that's why we started to blend it with the environmentally friendly citrus-based solvents. And in some cases we got good results, but in some cases we got worse result than the initial, because of this complex phase behavior that we have observed. I hope this answered your question. So we didn't increase the pressure to reach the miscible pressure and temperature of the carbon dioxide. And heating up was out of question, okay? Because we are looking for an environmentally friendly way. So heating up the reservoir means that you are generating steam. Steam was out of the question at all, because that the place that my sponsor is located, they are not tolerating any more steam in there. So because of the greenhouse gas emission, because of the carbon dioxide emissions, we could not play with the temperature at all. We could just play with pressure, and they said, no way, we will not able to play with the pressure. Okay.
Thanks, Dr. Berna.
Sure.
I have another question here typed from Brandon. And this is, how do the two citrus solvents affect the produced oil composition and its value?
This is a good question, really. So in terms of produced oil, what we have seen that because we have also here, I didn't show those results to you, but so here I have 60% oil and 40% initial water. Because of this initial water, we have realized in some produced oils emulsion formation. Even at room temperature that we were conducting these experiments, not heating up the samples, we have seen under the microscope small water droplets distributed inside the oil, but not in all of the oil samples. So while I'm just giving here the results, these results are actually giving, in terms of cost and in terms of quality of the produced oil, the better, lower viscosity, and also lower asphaltene content that we observed in these produced oils. However, if you're talking about like produced oil quality, if I just make the sulfur disappear, no, I am not God. So if there are some kind of components in the oil, there is mass balance, you cannot make them disappear by just injecting a simple solvent, but you can just change their structure and you can just move them to the heavier fractions. The only thing that I can say right now, we reduced the asphaltene fraction, the heavier fractions, and we created more aromatic hydrocarbons. Okay.
Right. Any other questions in the room?
So I
just one quick follow-up to Berna.
Sure.
What's the source of these solvents? How readily available are they?
It is extremely abundant. I am not sure if you are washing dishes. So I strongly recommend everybody to wash dishes. You will just get a lot of tips about enhanced oil recovery. So if you're dealing with a pan which is covered with oil, so you may have different tactics to just clean the oil. One of them is detergent, which we know as enhanced oil recovery, surfactant flooding. And the other one is just putting some water and heat it up it. And this is called hot water flooding in the EOR, or steam flooding in the EOR. Or you can just put lemon. So this is also stress-based, right? Lemon. I know from my grandmother, she was using orange as well to clean some oil wastes. Also, the other example is carbonate, the sodium carbonate that we are using in our while we are baking, and you can use it as a cleaning material. And this is known as in the EOR process another surfactant flooding, which is in situ surfactant flooding process known as. So these chemicals are extremely abundant, extremely easy to obtain, and also very cheap. These two, limonene and pinene. And if there is for example, in Florida, you know that their logo is also orange, right? In California, it is orange. Wherever you are seeing a lot of oranges getting produced, so they are producing these chemicals for cleaning purposes. Okay, so you are just buying it and cleaning and using to remove oil from your hands. I'm not sure if you have ever used WD-40. And WD-40 is extremely strong solvent, and it can remove any oil from anywhere. But WD-40 is toxic and extremely expensive. And the other alternative to WD-40 is truth-based solvents that you can find in Walmart, Lowe's, so in many retail shops you can find those chemicals easily, and they are cheaper than WD-40 for sure.
Thank you so much.
Sure.
No, great. Thanks. If there are no more questions, then I would like to thank Dr. Berna for the amazing presentation and sharing all the information in the slides. And the slides will be available on demand in our on-demand library. So if somebody has missed the session, then feel free to go to the SPE GCS on-demand content library, and you can download it from there, this recording of the presentation. I couldn't record the initial 2 minutes of the presentation, but hopefully that is okay. Last but not the least, this is the last luncheon that we have, and I would like to thank Jody, our chair, who's been very instrumental in making sure that all the events happen, even though we were in the pandemic. So thanks to her and the entire programs and publicity team for making it happen. And a big thanks, of course, to all the members and speakers who joined. Our next event is in September. It's the Reservoir Technology Symposium. So keep an eye out, and you will see those updates. With this, I'll close the meeting. Thanks a lot for attending, and have a wonderful weekend.
Okay, you too. Thanks for the opportunity. Bye.
Thank you.
Thank you, Dr. Berna. Thank you, everyone.
Sure. Bye.